That's cool. That's original. I haven't seen that before.
That's what I do when I'm teaching, so I
I've got it maxed
just use
out.
my boots.
Check, check. 1, 2, 3. 1, 2, 3. Check, check. Okay.
All good? Okay. Great. Hi, Susan. How are you? Ah, Susan, come hug. Yes. Yeah, I'm really looking.
Check. 1, 2. Okay. Thank you very much.
The restaurant, I'm guessing, but I don't know what time she's scheduled it for, so we'll find out, I guess. Oh,
All right, everyone, we're going to kick this off.
Yes.
It is my pleasure to introduce Dr. Elizabeth Brannon. She earned her bachelor's in physical anthropology at the University of Pennsylvania and her PhD in psychology from Columbia University. And she's now a professor at Duke University in both departments of psychology and the departments of evolutionary anthropology. In her lab, or should I say 2 labs, her research is focused on the cognitive development of human infants on one hand and non-human infants on the other. And in particular, her work examines both the evolution and development of quantitative cognition. Specifically, what do babies, whether human or not, know about numbers and quantities? How do they represent it without language? How do they learn about it as they grow? And some of her recent work is focused on how early training might facilitate mathematical abilities in children later. To get at this, she effectively uses all the methodologies, fMRI, EEG, behavior, electrophysiology. So she's taking this focus question on from all levels of analysis. And for her research in this domain, she's widely recognized and well-funded, for example, receiving James McDonnell Scholar Award, an Early Investigator Award from the Society of Experimental Psychology, an NSF Career Award, and continued grants from both the NIH and the NSF. And so today she's going to tell us about developmental and evolutionary foundations for the human mathematical mind. Please join me in welcoming Dr. Elizabeth Brannon.
Thank you. Thanks so much. And just one minor correction is that I'm now at Penn. I was at Duke for a long time. That's okay. And you'll hear one peril of moving from universities in my data towards the end of the talk. Okay, so I'm really pleased to be here. I've been having fascinating conversations this morning, and this is a powerhouse of numerical cognition. So wonderful to be here to talk with so many of you. So as you all know, whether we are counting or paying or labeling or measuring or timing, we are using numbers, and our complex civilizations would not be possible without numbers. And much of this is uniquely human. No bird or rodent or monkey will ever design a skyscraper or send a mission to the moon or even open a grocery store, right? But in addition to these uniquely human numerical capacities, we share with animals a primitive sense of number. And my work studies this primitive number sense with many different methods, as Talia mentioned, some of which I'll talk about today, and multiple species and a developmental approach. And I use number as a paradigmatic case study for studying complex thought without language. So I want to understand how number is represented in the brain, what we share and what we don't with other species, how our representations change over development, and how the primitive number sense may or may not scaffold uniquely human symbolic mathematics. So what do I mean by this primitive number sense? Well, I mean the kind of representation that animals use when they do a task like this. So this is a monkey, a rhesus macaque, ordering numerical values, ordering stimuli based on their numerosity. So she's starting each trial by touching the bottom right open square there, and she's ignoring the size of the yellow background, the size of the individual elements, their shape, their color, their configuration, and she's choosing the smaller one and then the larger one. And she's getting a little squirt of juice after each correct response. If she had made an error, the screen would have turned black, but this is a very well-trained monkey, so she has not made any errors. This is a ring-tailed lemur doing the same task. He's using his nose, but otherwise it's the same thing. He's choosing the smaller and then the larger, and he's getting a little food pellet at the bottom of the screen. So when animals make these kinds of judgments, their performance is ratio dependent. So here you can see accuracy and reaction time as a function of the ratio between the two numerical values. And you can see that accuracy approaches chance as the ratio approaches 1, and reaction time increases as the ratio between the two numerical values approaches 1. And you can also see that humans, these are Duke College students, in the same task perform very similarly. So if we tell them not to verbally count, of course, and we give them the exact same task with the same stimuli, their performance looks very similar to monkeys. Of course, if they were verbally counting, their performance would be at ceiling, but we can strip away this uniquely human symbolic system by simply telling them to respond quickly. And we see similar ratio dependence in infants. So this is a study by Fei Xu and Liz Spelke using the visual habituation procedure. And they used stringent stimulus controls that hadn't been used in the field before this study, and showed that 6-month-old infants could discriminate 8 versus 16 dots, but could not discriminate 8 versus 12 dots. And I'm going to show you another example of this with a different paradigm, making this point of ratio dependence. So here, first, just watch the infant's eyes, and you can see his attention is getting attracted to the center stimulus. And if you watch his eyes, you can see he is moving back and forth, looking back and forth between these two streams of images. But he then fixates on this one, and he continues to fixate on this one. And if you now look at the stimuli, you can see that this is alternating between 10 and 20 dots, whereas this stream is a constant 10 dots. So for other infants, this would be a constant 20 dots. And infants in this procedure prefer to look at the changing stream. Always have to wait for that little response there. Okay, so this is data from 4 different groups of infants, and you can see this was the 1-to-2 ratio that you saw, and you can see that infants in any of these ratios show a significant preference for looking at the changing stream. But when it's a 2-to-3 ratio in the changing stream, they do not show a significant preference for looking at one screen or another. Here we see that the same kind of ratio dependence holds, and that the magnitude of the preference scores increases with the ratio in the changing stream. We also see that these primitive number representations can enter into arithmetic computations. So here you'll see part of Jessica Cantlin's dissertation work. The monkey monkey initiates each trial and now keeps track of the number of dots behind the includer. So sometimes it's a subtraction operation, and sometimes it's an addition operation. And the monkey has to choose one of two arrays that is equal to the difference or the sum of the operation. And obviously, numerals are just for you. The monkey doesn't see that. So what we see in this task again is that accuracy is dependent on the ratio between the correct choice and the distractor, the incorrect choice. So the monkey would not be able to answer these questions with very precisely if the two values differed by 1, but when the ratio is favorable, the monkey can keep track of these addition and subtraction operations. We also see that these representations are independent of the sensory modality in which they're experienced. So here you can see a monkey doing a match to sample task where the monkey has to match the number of things they see or the number of things they hear in sequence on other trials with the numerosity of the visual array. So I didn't hook up sound because it's just beeps, but on some trials there would be no visual sample, and it would be a sequence of tones, and we can vary the intertone interval, the length of the tone, etc. And the monkey can choose the visual array that matches the number that they have heard. And what we see in that task is that accuracy is actually very similar regardless of whether the sample was visual or auditory. So there is a reaction time cost that I'm not showing here, where they're slightly slower when the sample is auditory. But in terms of accuracy, they're able to match across sensory modalities, and there's no cost. And we see parallel results in infants. This is a study with Liz Spelke, where infants using a different procedure and phoneme perception also show ratio dependence and match across sensory modalities. So that was a very brief overview of what I mean by this primitive number sense. And what I want to do today is two parts. First of all, I want to ask whether number is a primary stimulus feature or whether it's derived from more perceptually grounded representations, and tell you about some of the work that we've been doing that addresses this question. And then I want to switch to the second question of the relationship between our shared primitive number sense and uniquely human symbolic mathematics. So historically, the animal learning and cognition community largely considered the representation of number to be something that animals could be trained to do in special circumstances, but something that was akin to a circus act. So we can train a chimp to wear a suit, but obviously this is not ecologically relevant for them. Similarly, Piaget argued that children initially attend to other features, such as the length of the line of this line of coins, for example, and that only with education and development do children come to appreciate number as an important dimension. More recently, a sensory integration perspective has been emerging. And here, the idea is that since numerosity can be mathematically defined as the product of density and field area, or by the total surface area of the items divided by the mean item size, that decisions on numerical quantity could be derived indirectly on the basis of representations of these non-numerical properties without numerosity being encoded by perceptual systems. And in fact, this line of reasoning and this perspective has actually been used to challenge the very existence of the approximate number system or the primitive number sense. An alternative perspective that I'll argue for here is that number is actually a primary property of the image that is directly perceived through specialized and dedicated mechanisms. So although numerosity can be defined as derived from other perceptual continua, we can model it that way and define it that way, I believe that evidence is accumulating that this is not actually the way number is represented. So I'm going to make that argument with these different sources of evidence. So the first one is that I believe there's abundant evidence that babies, children, and monkeys perceive numerosity spontaneously. So there are studies that look at this in more spontaneous preparations. So in the wild or in baby chicks who have just a day or two of experience to look at spontaneous numerical discrimination. But of course, the challenge with these kinds of approaches is stimulus control. So in the laboratory, we can control for all of these alternative stimulus dimensions, or at least assess their contribution to decision making. But laboratory studies have been criticized for requiring thousands of trials of training. So how do we know that it's spontaneous and not some circus act like the chimpanzee wearing a suit? And so there have been different approaches to get at this issue. So this is way back to my dissertation work. You can see a monkey again doing this kind of ordering task. And what we showed here is that monkeys that were trained to order particular numerical values transferred to novel numerical values. So they were able, without any reinforcement, to order numerical values that they had never experienced in the laboratory. And in fact, performance was controlled by the ratio, not by the familiarity of the particular numerical values. So they could be better at two novel values as long as their ratio was large. So that's one way of thinking about this aspect of spontaneous number representation. Another way is to ask what happens when a monkey or a child is faced with a problem in which they can solve it by number, or they can solve it based on some other continuum, and then we ask which one of these is actually controlling their responding. So in this study that Jessica Cantlin did, monkeys and children and adults were trained in a task where surface area and numerosity were confounded in a match to sample task, and then we pitted them against each other in a choice where one of the stimuli matched based on numerosity and the other matched on surface area. And what you can see is that when the ratio was large, and until it became very close together in numerical value, that monkeys and children and adults preferred to use the numerosity rather than the surface area in these arrays of objects. In infants, we used this same change detection procedure that I showed you to ask the same question about the relative salience of numerosity and cumulative surface area. So we're going to get at the question of when numerosity is changing on one side and area is changing on the other, which one the infants are attracted to. But before we do that, I'm just going to show you what happens when we just look at an area change versus no change. So I showed you in the video a numerosity change versus no numerical change. Here's data from an area change versus no change at a constant numerosity on both sides. And what you can see, I showed you previously that the infants needed a 1-to-2 ratio to notice this difference in numerosity. You can see that for surface area, infants need somewhere between a 1-to-3 and a 1-to-5 ratio change. So they show a significant preference for the changing side when it's a 1-to-5 ratio change. So that's just to put this data in perspective. So over here, this is a numerical change on one side and a surface area change on the other. And the numerical change is always a 1-to-3 change, but the surface area change is 1-to-3, 1-to-5, or 1-to-10 in these three different groups of babies. So what you can see is that babies prefer the number change when it is the same ratio change on area and numerosity, and even when the area change is much larger, a 1-to-5 ratio change. And by a 1-to-10 area change, they no longer prefer the numerosity side, but they don't show a significant preference for the area changing side. So these data suggest that by 7 months of age, infants are already finding numerosity to be more salient than surface area. And an important caveat here is that this is only when we're talking about an array of objects, right? Infants can do a 1-to-2 ratio change when it's a single object. It's that when babies are looking at an array of objects, numerosity seems to pop out. Okay, so in nature, many dimensions are correlated with numerosity, and it's been notoriously difficult to ensure that animals or babies, especially babies with our limited number of trials in any session, are attending to numerosity rather than some other stimulus attribute. And there have been many different approaches and to try and examine this. And Nick DeWind developed a novel approach. Instead of attempting to rule out alternative dimensions by controlling for them in different blocks of trials, for example, he orthogonally varied all these variables and used a regression approach to model the acuity of the numerosity judgments, but also the degree to which judgments are biased by any of these other stimulus dimensions. So here's a data set where he used this approach. So children and adults are shown two arrays and asked to make either a numerosity judgment or a surface area judgment. These are 5-year-old children, so about kindergarten age, and they're given these cute instructions. So for example, Dino wants to fill up lots of space in his tummy. Can you choose which dots will take up lots of space in his tummy for the surface area description? And we gave adults those same descriptions just to be, just to make sure the reviewers were sure it was the same. Okay, so here's what we get in this kind of a task. First of all, not surprisingly, adults are more accurate, so they show better acuity than children. But more importantly, we see that adults and children both show better acuity for numerosity than for cumulative surface area of these arrays. And in fact, we see over here that there is very little influence of surface area on numerical judgments. So for adults, it's not significant. For children, it is significant, but it's much smaller than the parallel influence of numerosity on their surface area judgments. And there is another beautiful data set that I think Steve Ferrigno might be here. There he is, okay, from this group of folks that have looked at this in monkeys, children, Tsimane adults, so a farming community in Bolivia that counts late in childhood, and adults. And the main point of this paper is very similar to the points I've been making, but they show it really beautifully here, where they show that numerosity is controlling responding in this bisection task, much more so than cumulative surface area. So even without language, numerosity is perceived spontaneously and is more salient than other dimensions. And numerosity interferes with area judgments more than the reverse. So if the sensory integration theory holds and number is derived from continuous variables, then we should see earlier processing of these continuous variables compared to numerosity in the processing stream. So to test this, we used the same stimulus space and analytic technique that Nick DeWind developed, but in this case to ask about the neural signals for continuous variables versus numerosity in terms of the temporal stream of processing. So this study was conducted by Junku Park and Nick DeWind, and it's an ERP study. And here, number and size and spacing of the elements within an array are orthogonally varied, and numerosity is ranging to the same degree that all of these other dimensions are varying. And the task is passive, so the participants are doing a very simple target detection task that has nothing to do with numerosity, and they are observing these arrays pretty rapidly. And we're then using a linear model to quantitatively assess the influence of variations in these different visual properties on the ERPs of the participants. So if number is derived from other visual properties, then we should see that ERPs that are uniquely sensitive to other visual properties, we should see these earlier, at earlier latencies than numerosity. So what they found were two different peaks that showed numerical sensitivity. So first of all, a parieto-occipital peak around 220 milliseconds, which is similar to ERPs that have been shown to be distance-related in many other studies. And here, the cyan color is the smallest numerosity, and the magenta is the largest numerosity, and the green line is the linear contrast, so you can see where it's significant. And you can see that the functions fall apart based on numerosity very systematically. We did find at this latency that the data also showed some sorting based on continuous variables, but this was to a lesser degree. But more importantly, we also found this very early peak modulated by numerosity. So at this medial occipital channel, just 75 milliseconds after the stimulus presentation, we see numerical sensitivity. So again, separation here by numerosity. And we don't see the same kind of sorting based on these other dimensions, size and spacing. So this was very surprising to us that we saw this occipital extremely early numerosity sensitivity. And so we've been continuing to look at that using functional imaging methods as well. And so this is convergent evidence that I'll show you for this occipital, this very early occipital numerosity selectivity, but it's also addressing this question of mandatory processing, or how mandatorily we may or may not process numerosity. So this is a functional imaging task in which participants are seeing the exact same visual arrays, but have to either make a judgment about numerosity or about color, about the redness of the arrays. Here we're exploring the role of attention. So our question is whether we can decode the numerosity of the first stimulus based on the bold response in these blocks where participants are actually attending to numerosity versus these other blocks in which they're attending to color and not numerosity. So first, Nick derived subject-specific regions of interest using a localizer task. So this is a task that identifies number-selective regions over and above, for example, face processing. And then he also defined anatomically, using a probabilistic retinotopic map that Sabine Kastner developed, defined all of these different regions. So in red, you're looking at early visual cortex, so V1, V2, and V3. And then all the way in blue, you're looking at multiple regions that are interparietal sulcus and superior parietal lobule areas. So these regions of interest across the dorsal visual stream were defined. And the question is whether we can return the numerical value of the first stimulus using support vector machine linear classifiers to decode the numerosity of the stimulus. So what you see here is that we can in fact do that in all 4 of these regions of interest in the numerical task, so when subjects are actually making a numerosity judgment. And we also can decode numerosity when subjects are making a color judgment task, so when they're not actually attending to numerosity. We actually, I don't show this here, but we ran another whole group of subjects that only did the color task so that there was no bleeding over from the number task. We actually made sure that the consent form said nothing about numerosity, et cetera. And we still can decode the numerosity of the stimulus when subjects are engaging in this color task. We can also cross-task decode, so we can use the neural responding from one task to decode the numerosity from the other. Okay, so in the sense that encoding of numerosity does not depend on attention to number, our finding supports the hypothesis that numerosity is direct and automatically extracted during, in this case, visual perception in both early visual cortex and the interparietal areas. Okay. So I'm going to pause for a minute and see if there are any questions. But first, to just summarize this, I've given you these different sources of evidence that number is not a last resort strategy and that it does not seem to be a secondarily derived feature, but instead is more of a primary feature. Now, I just want to say a little bit more about what I mean by that. Some of you might be familiar with David Burr's work where he has shown that when you adapt individuals to an array, a large quantity, that there is strong underestimation after this adaptation, regardless of things like dot size, contrast, spatial frequency, density, and shape. So over a wide range of conditions, ensembles of objects are subjectively experienced as a specific quantity of items or an approximate quantity of items, irrespective of other correlated perceptual features. And in fact, this adaptation that David Burr has shown also works cross-modally. So I think collectively, these sources of evidence from our lab and from many others support the idea that we are more directly perceiving number and that we're not deriving it from these other modalities. Yeah, Talia.
I was surprised by the early visual cortex results.
Yeah.
I can see in behavior you get the sense of it being numerosity, but you might not have expected every neural region to have that. Like maybe early ones would show sensitivity to surface area more, and later ones, so
Yeah.
I was wondering, was that what you expected, and how do you make sense of that early, in particular that early visual cortex?
Yeah, it's a really good question, very important. And it's not what we expected initially, but we've now found it in 2 fMRI data sets, and Evelyn Egger has found it as well in Stan DeHaan's group. And so we think it's really there. But initially, we certainly thought that it would, we also thought that it might, so I think a really important question is whether when we do this task cross-modally, which we haven't yet done, whether we'll then see parietal and not early visual cortex, we would expect, right? So we didn't expect it to be this early, and we didn't expect it to be this tied to to visual cortex, but it is, yeah. Yeah, follow up on that.
I wondered if you thought about taking into account the visual factors with respect to cortical magnification. So not just matching them in like pixel area, but thinking about how different bits might be expanded when it gets magnified through fovea and decreased in the periphery, and maybe there might be signature there.
That's fascinating. I have not thought about that at all. I'd love to talk to you about that and see how we could do that. Yeah. Yeah, Susan.
Of course, you know that I'm completely agree with number being a that the dedicated input analyzers that encode number and what they're interested in number. But they still have to do it on the basis of some computation over lower sensory features, not necessarily lower perceptual ones. How do you think that what are the representations and computations like that are yielding these approximate number representations? I mean, I didn't ever see the sensory integration alternative as a real alternative.
Mm-hmm.
If it turned out that the way we spontaneously represented number was to combine information about surface area and density.
That wouldn't be a problem with the, right, sure, right, yeah.
I know that you could try to then make it deflationary as they did.
Yeah.
Right? But how do you think they're doing it?
Right, so this is a really important question, obviously, yeah. So I would love to show you my computational model of exactly how number is derived neurally and how it becomes behaviorally what we see, and I don't have that. In terms of, you're right that in visual areas, we certainly expect to see, we were very surprised not to see sensitivity to continuous variables in early visual areas. Now, when we just present, again, back to the behavioral parallel, when we just present a single dot, we obviously would see the ERPs, for example, systematically vary as a function of size. And so we absolutely expected to see that. But when we look at visual arrays, we don't see it at all because we're talking about the cumulative surface area. But we actually even see some dampening when we try to look at the individual element size within an array. It seems that there's some dampening of responsivity as a function size of an individual element when it's in the context of an array. So, it's hard to understand how 75 milliseconds into the processing stream that we're already seeing numerical selectivity. But again, to the best of our ability, we're controlling for all of these dimensions. And so it seems as if it's being directly pulled out. It's not magic, that's true. Yeah. So I'd love to hear people's ideas of how that could be happening. Yeah, Liz.
I just wondered whether you think the Jahan-Schrödinger model may have actually predicted that is, that you have a purely visual process of normalization by size that leaves you with a representation of where there are things in the array but not what their sizes are, and then some process that's done.
Right. Yeah, so they expected it to be later, but they did, right. And I guess the other question, we know behaviorally that, that the representation becomes amodal or cross-modal, right? And so this, in some ways, is unparsimonious. It suggests that we have different systems for extracting it from different sensory modalities, but that does seem to be what this suggests, yeah.
And then just a question kind of for looking ahead to future research.
Yeah.
Really fascinating to see whether that early peak is actually functionally relevant in some way. That people who have a stronger peak show higher ANS acuity or something.
Yeah.
Actually connected it to behavior to dispel both to dispel any potential remaining worry about could there be some other way of looking at these stimuli that could account for this other than number.
Right.
Or to maybe shed light on what the computational process is.
Yeah, absolutely. So we do know that that later parietal ERP is correlated with acuity in ANS acuity. So the question is whether the earlier one is. So yeah, very important question. Okay, so I now want to turn to the second question, and this is an important question, the relationship between the approximate number system and symbolic mathematics. It's a broad question. It's important for both basic science reasons and basic science reasons to allow a more complete understanding of both the evolution and the development of this important, uniquely human symbol system, but also potentially for informing educational policies. So the approximate number system is just that. It's approximate. It does not allow exact representations of number. And this is obviously distinct from our uniquely human system for representing number, which allows precise representations. And we know by the age of 4.5 or 5, children in industrialized societies have learned the verbal counting system, that they've become cardinal principle knowers, such that they appreciate that the last number that they use in a counting sequence indicates the quantity of a set, and that they have mapped these representations on to symbols for number. Susan Carey's book, which many of you are probably familiar with, this important book describes this conceptual change, this really major change that happens when children learn the meaning of number words, and offers an account of the initial representations that children use as they learn the verbal counting system and become cardinal principle knowers. And in this account, they use object file representations derived from this kind of a search task and others, the evidence derived from this kind of a search task and others. So I just wanted to make kind of the connection between this question and what I'm focusing on clear, that right now I'm not asking about the initial representations, but asking about the role that ANS representations play in our symbolic representations of number, and whether they serve any role as children are learning about symbols for number. So it may surprise some of you to read this quote by Rafael Nunez, where he makes the analogy that the approximate number system and symbolic math are about as related to each other as snowboarding is to bipedalism. So this is kind of a straw man here, but there are perspectives that exist that the approximate number system and symbolic number representations have no relationship to each other. That we could not snowboard without bipedalism, but that snowboarding is completely unrelated in terms of its evolutionary origin, clearly, or lack thereof. Okay, so I don't know if I may only do the first and the last of these because of time, but these are the different sources of evidence that I wanted to talk about for the idea that the approximate number system in infants that we're looking at is making connection with the symbol system for number, for uniquely human mathematics. So first of all, there is a lot of evidence at this point that ANS acuity, that the acuity of this primitive number sense system correlates with symbolic math performance. So this figure from Justin Hilberda, Michelle Mazzocco, and Lisa Feigensen's study shows us that the Weber fraction, our quantitative assessment of numerical acuity, correlates with two different measures, standardized measures of math. This measure was taken at 14 years, and this could be anywhere from 5 to 14 years and holds even when we control for IQ. So this is the test of early mathematical achievement and the calculation portion of the Woodcock-Johnson task. And in fact, there have been 3 different meta-analyses of data like this, and while it accounts for a small amount of the variance, thankfully, in symbolic math performance, it is a significant effect in many data sets. We also see that in individuals that have severe deficits in symbolic number representation, so dyscalculics, that ANS acuity is lower. So here you can see in red 10-year-old dyscalculic individuals compared to age-matched controls, 10-year-olds, or math-matched controls, 5-year-olds, and you can see that the dyscalculics show much worse Weber fractions. And I think I'm, well, okay. So the third source of evidence suggests that ANS representations are linked to number word representations before children become cardinal principal knowers. So again, this does not mean that they are the initial representations that children learn, that children use, that they map onto when they're learning the meaning of number words, but it suggests that this is happening before they become cardinal principal knowers, and therefore that it may play a role in how they are learning about numbers. So this is an EEG study that Michal Pinhas conducted that's based on a variety of EEG studies by Angela Frederici that used congruency of objects and number words. So basically, children hear a number word and they see a number of objects, and sometimes it's congruent and sometimes it's incongruent. And our question is whether we see a neural incongruency response, but more importantly, whether that incongruency response depends on the distance between the number that they're actually seeing and the number word that they're hearing. So the same children were given a given number task, which assesses their understanding of the cardinal principle and how well they understand how verbal counting works to achieve the number in a set. And what we see in this task is that we can find incongruency responses, so ERPs that differentiate the congruent and the incongruent trials at 2 different time periods. So a negative polarity centroparietal response between 200 and 500 milliseconds, but the one you'll see in the next slide is a positive polarity incongruency response that's later, between 700 and 1,000 milliseconds. And this one shows separation as a function of numerical distance. And more importantly, the data you're looking at here is just in subset knowers. So these are children who do not yet understand the cardinal principle, and you can see that nevertheless, the incongruency response is distance related, suggesting that they're appreciating the degree to which the number word and the visual set differ and suggesting that these might be approximate number representations, this graded positive incongruency response. Okay, but I want to focus on this last question of the causal relationship between the approximate number sense and mathematics. All right, so first of all, we know that the acuity of the number sense improves over development. So in the newborn study that I briefly flashed earlier from Liz Felke's work, we know that infant newborns can do a 1-to-3 ratio, and that this improves over human infancy. And we know from these data from multiple groups, but especially this amazing, massive data set from Justin Halberta, that acuity continues to develop all the way into our mid-adulthood. We also know that acuity of the ANS can improve with training, that it is susceptible to training effects. So this is just one example of that, where acuity accuracy increases from session 1 to session 6 of repeated numerosity training. So this brings up the question of the causal relationship. So everything I've shown you before is correlational, and the question is whether there is a causal relationship. Can we actually improve this system, and will that have any effect on any aspect of symbolic math performance? So if I were giving this talk about a year and a half ago, I would say that we have really strong evidence for this, not just in children, which I'm going to show you, but also in adults, which is very surprising. You're about to see the perils of moving universities. So Jun-Koo Park developed a task where he gave participants, college students, a pre-test and a post-test on symbolic math and a variety of control tasks, and trained them to do approximate addition and subtraction, or multiple different control tasks. So here's the actual experimental task in this video. So they see a number of dots go behind the occluder, and they have to determine which is correct, which is the sum, or whether the sum is greater or less than this amount. And the same thing for subtraction. So it's quite challenging. The task is titrated. They come in day after day over many sessions, and they get much better at this task. So they show clear improvement. And we compare it to a variety of different control training tasks. And we had 3 different groups of independent participants collected at Duke, where we thought the story was very clear. So in red are participants who were trained in the approximate arithmetic task you just saw. In pink are subjects combined that were doing anything that was numerically related but was not the approximate arithmetic task. And in gray is a no contact control and non-numerical control tasks, including short-term memory. So we thought we had very clear evidence that the gain in symbolic math, the post-test score being better than the pre-test score, was true for approximate arithmetic training above and beyond any of the controls that we could come up with. But, full disclosure, with much larger sample sizes at Penn, you can see that this result is not there. And some of this data is a very direct replications using the exact same programs. So in some sense, this isn't surprising that for adults who have already mastered 2- and 3-digit addition and subtraction, that their fluency in this task would not be influenced by engaging in a few sessions of approximate arithmetic. But where we were a lot more optimistic about this, and where we thought the effect would be more likely to be important, is in children. So, of course, we know that the achievement gap in the United States is profound and persistent, and that low-income children enter kindergarten with much worse symbolic math skills. They don't know the meaning of number words. They learn them at a much later age, both in terms of the words and the symbols. And they're getting much less math input in terms of math language at home. So if we could harness this system to improve math readiness in young children, this would obviously be extremely important. And it would tell us also about the relationship between these two developmentally. So we first developed a simple adaptation of the adult task for children and a control memory task. And we found that children who were trained in the approximate arithmetic task showed a higher gain score in the test of early mathematical achievement compared to children who were tested in, who were trained in a memory game. And we found this in a second group of preschoolers as well. And there have been multiple other studies from Liz Spelke and Dan Hyde and others that have also shown similar effects in young children where engaging in different types of approximate number system games, addition and subtraction and ordering, seems to benefit their immediate symbolic math performance. And in this Herculean study with 1,500 Indian preschoolers, we see also that there is an immediate benefit, and by immediate, we're talking 1 to 3 months later, right? So very much replicating these other studies of approximate arithmetic and a more heterogeneous intervention of intuitive math and spatial skills. But interestingly, a caution to this is that the training did not improve symbolic math performance a year or so later. So we're still, as a field, trying to understand the significance of these kinds of benefits. Now, one possibility is that training, some different kinds of approximate number system training are actually sharpening the ANS representations so that they're yielding less overlap in the subjective representations of numerosity. And this might give children a stronger foothold into the exact integer system and learning and mastering the meaning of number words if they're using multiple sources as they learn the meaning of number words. And more confidence may lead to deeper engagement, more spontaneous attention to math and numbers. So there's a lot of possibilities for how this might actually be functioning. And we've been exploring a possibility that there's also an important aspect to overlap in the cognitive algorithms, so that the functional isomorphism between the addition operation in approximate arithmetic and in symbolic arithmetic is what's facilitating performance in these tasks. And so that has taken us in another direction to look at other operations. So for example, ratio reasoning, where children have to choose which gumball machine is going to give them a better chance of getting a red gumball, for example. And they have to do this either in a non-symbolic way or in a symbolic way. So those are two different tasks that the child could be faced with. And we see that performance on these two tasks is correlated. So these are first and second graders, I believe. And so these are children who know the meaning of these symbols that we're using, but their performance is correlated on the two tasks, but they're much better on the non-symbolic, or significantly better anyway, on the non-symbolic version than the symbolic version. But what we're finding, consistent with this idea of operational specificity, possibly, is that engaging in the non-symbolic task first facilitates performance on the symbolic task. So if we just look at performance on the symbolic task, children who engaged in the non-symbolic task first do better on this symbolic task than children who are thrown right into the symbolic task. So it's possible that, that we're seeing this kind of operational facilitation. So that's something we're exploring now with division and multiplication and a variety of other non-symbolic operations. And the final thing that I want to mention is that we're also finding overlap in the brain regions that are recruited when individuals engage in both non-symbolic approximate arithmetic and symbolic arithmetic. So in this functional imaging task, adults engaged in either symbolic addition, non-symbolic addition, or a control task. So for the dot task, it was identical, and they were making a color judgment. And for the addition task, we did letters so that they wouldn't spontaneously make these calculations with additions. So what we found, so we predicted, first of all, that we would find bilateral interparietal sulci, a region known to support magnitude representations, that this region would be recruited in both of these kinds of operations, in the addition operations and not the control tasks. We found that that a larger network of areas, so bilateral IPS, the right superior parietal lobule, and the bilateral inferior temporal cortex, all came out in the conjunction of these two addition tasks. But more importantly, using a representational similarity analysis, only the IPS elicited stronger similarities in the neural activity for these two tasks where people are engaging in addition compared to their more physically similar control tasks. So again, support for the idea that this could be one possible mechanism for the reason that we see this kind of facilitation. So in conclusion, a challenge for cognitive science is to understand how we go from this initial state to the adult state, to doing something as mundane as counting the number of sheep in a field, or something as spectacular as winning the field medal or the Abel Prize in mathematics. So what are the crucial ingredients that make this possible, and what do we build upon? And this is obviously a very complex question that there are many answers to at many different levels. And the argument that I've made today is one of evolutionary and developmental continuity. So approximate number sense representations are of primary relevance to us. They emerge early in development, but also in our neural processing stream. Number is salient, and we're often better at representing it than continuous variables. And while there's still much to figure out in terms of how number is computed and represented in the brain, models must work with the constraint that these number signals are emerging early, and sometimes even before signals for continuous summary aspects of a stimulus. So non-symbolic representations of number remain throughout the lifespan, despite the emergence of human math symbols. And the isomorphism between the symbolic and non-symbolic mathematical operations that we engage in may be educationally useful because of their shared neural overlap and shared computational processes. So thank you very much for listening, and I'd love to take questions. Yeah.
I really liked your analogy, or maybe it was a straw man, about the walking and the snowboarding.
Okay.
Right?
Tell Raphael.
In your examples of why numerosity and symbolic mathematics is different, by trying to do the same experiments in my mind, comparing snowboarders and walkers. And I think you would get exactly the same correlations. You would find first the people who walk faster, run faster, also snowboard faster. You might learn that people who get trained to run also show an improvement in snowboarding. And even at the level of brain imaging, you might actually find very similar results. So I guess my question is, what is the most convincing of the last examples you've shown that numerosity and symbolic math is really much more closely related than walking and snowboarding?
Well, so we know that snowboarding obviously only exists in certain societies and is a cultural invention that is not something that it emerges in all societies. In contrast, we see that symbol systems for number exist in almost all societies, right? That already shows us something fundamentally different about the two, right? So you're asking me which of the many sources of evidence that I attempted to marshal is the most convincing that approximate number system representations are tied to, because of the correlation would exist in both. So, right, so we certainly thought that the most important tactic would be the causal connection, and we do see it in children in many different samples now, okay?
But that would also work for snowboarding, right?
We don't know. That's an empirical question. I don't think teaching somebody to run a marathon would necessarily transfer to snowboarding. I mean, it's an
Well,
empirical
it's very
question.
okay. But generally training, exercising vigorously, if I'm running, I think my snowboarding skills will be...
well, it would probably be more due to cardiovascular health than specific issues with snowboarding. So the athletes in the room must, there's lack of transfer across many sports skills as well. So, right.
But we might very well see it.
Yeah. Yeah.
I think
So
I'm just saying that I guess
Do you have another idea of how one could test this in other than a causal design, a training design? Is there another way that would be more compelling to you that would show you that would make you believe the relationship
I
between?
think what you showed at the end when you trained them specifically to a task that doesn't just get like performance capacity.
Uh-huh.
What I found really convincing is the memory task, training children on a memory task,
Uh-huh.
and training children on a numerosity task, and showing that one helps and one doesn't.
Right, right.
For the symbolic one, I think that is something that I found really convincing, because it doesn't just get to the training the agent in a general capacity, performance enhancing capacity,
Right.
and showing that
Absolutely, and all of the designs is attempting to have control tasks that compare. Yeah.
Hardest part is picking the control.
The right control task, that's right. And we can always say that there's some other control task we need to do. Yeah, Liz?
Yeah, I mean, another source of evidence other than training studies that maybe is relevant to this point
Yeah.
is studies that we did a long time ago, but recently I think are replicating now in India on a much larger scale with kids, where we take kids who learn to count to 100, and they know the meanings of all of those words. At least they know that like 78 is bigger than 32. And so
Right.
forth. And ask them to do approximate addition. So we give them addition problems purely symbolically. So this kid has 22 marbles and gets 30 more, and this other kid
Right.
has 70 marbles. Who's got more marbles?
Mm-hmm.
And the kids initially say, I haven't learned arithmetic yet, I can't answer that question. We say, that's okay, just guess. And kids' guesses show all the signatures of the approximate number system, right? They guess better if the ratios are more different and so forth. I don't know whether that helps, Florian, but I think maybe tasks like that. And training studies, the great thing about training studies is they establish causality. The really annoying thing about training studies is that to train anything, you have to train lots of things. And you don't know which of those
Right.
lots of things that you're training are actually doing the work.
Mm-hmm. Mm-hmm. Yeah. Yeah.
In continuing this discussion, once I volunteered to train in tribal area in India, mathematics with one of my friends from Department of Mathematics.
Uh-huh.
And not only personally me and my friend, but my friend and I, but other people who are collecting data on the tribal people particularly, tribal means who dwell in forest till now.
Mm-hmm.
Their kids still find it quite difficult to understand the concept of dividing equally. So given this much of fruit to you and you divide equally, the first person takes more than equal division, and no other kids find it surprising.
So there's a social factor involved there, though. Yeah.
We find really difficult to understand, and then we later understand they're correlating with the number of family members.
Ah, uh-huh. Yeah,
Training is
that's fascinating. Yeah, so they're not unable to divide equally. It's just that there's these other social factors that are influencing the rules of the game for them. Yeah, absolutely. Yeah, we have a division task where children who don't understand the division symbol at all are very flexibly dividing and understanding that all of the sets need to be equal. Yeah, so, but there's no social structure aspect of this. It's a bee and pollen scenario. So the social structure, yeah, can interfere with these kinds of decisions, yeah. Okay, thank you very much.